Hello, my name is Sandy Earl, as you know, and we are going to use a very powerful tool to solve some problems. So we're going to solve complexation problems using a linear approach. So, as you know, I'm going to advance the slide here. Not sure exactly what you're seeing, but we're going to first use this to solve cyclodextrin solubility problems. Remember, cyclodextrin is that cool donut that we can use for lots of things. And I call it an invisible cloak, invisibility cloak, where you can actually put molecules inside this structure and be able to mask taste, be able to make things more soluble, which is what we're going to be looking at today, and has lots of applications. So what we want to know is how much cyclodextrin we need to add to get the concentration that we need of our drug. So maybe we can't get a concentrated enough solution without adding this invisibility cloak called cyclodextrin. So we can solve that problem. We can know how much cyclodextrin we need to add in order to have the concentration that we want to get of a particular drug, as long as we understand the relationship between the cyclodextrin and solubility. So first thing we're going to do is solve these cyclodextrin solubility problems using the linear approach. Now, remember, again, I'm not sure what you're seeing, so I'm going to remember that the relationship between the drug concentration that we see and the concentration of beta cyclodextrin we need is a linear relationship. As we increase the concentration of the beta cyclodextrin, as we put more of these little donuts in, we can improve the solubility and therefore increase the concentration of the drug. So as that concentration of the invisibility cloaks increases, we can also increase the concentration of drug. So it will form a linear relationship with the slope showing the relationship between how much we have to give to get a certain concentration. Now, where this drug concentration is at zero, when we have zero of those invisibility cloaks, this would be at the 0 point, which is this point right here, or this point right here. That would be the innate solubility of the drug. The innate solubility of the drug is the maximum solubility of the drug with no beta cyclodextrin, no invisibility cloaks are in the solution, so it's just the drug by itself, what the solubility would be. That's what innate means, right? So the innate solubility of the drug is at that D0 point, which is right here. Okay? So if we take the relationship and put it in a linear form as we have here, so the drug concentration, so how high we can get this drug concentration is going to be equal to the innate solubility, or D0, which is the y-intercept, right? So y equals mx plus b. So this is the y-intercept, or the innate drug concentration. The x is going to be the concentration of beta cyclodextrin we have. So this is our x. This is our y, this is our x, right? And then the slope of the line here is this whole mess here, which is a relationship between the affinity constant and the innate solubility and another constant. So this is the slope of the line, which doesn't really tell us much because it's this big mess. But we know that the x, which is the concentration of drug, and the y, or the concentration of beta cyclodextrin, and the y is a concentration of drug, and the innate solubility, which is y, and then they'll have this relationship here. So we can put in any particular concentration of drug or concentration of beta-cyclodextrin, and as long as we know the innate solubility and the slope of the line, we can figure out the other, either the drug concentration or the beta-cyclodextrin concentration that we need. So you can see that this is a powerful tool. Now, that the slope of the line is determined by that crazy relationship. But the good news is we can get the affinity constant, or Ka, putting in the slope of the line and dividing it by the y-intercept times the quantity 1 minus the slope of the line. So we can determine the affinity constant. So we can compare two affinities of two different drugs for that beta-cyclodextrin. So the higher the Ka, the higher the affinity. So we can get a lot of useful information from this linear relationship. But what does it mean? Or how do we get it? So if we have beta-cyclodextrin concentrations here, and the resulting drug concentration, in this case, it's paraminobenzoic acid. So when we have 0.5 millimoles per liter of the beta-cyclodextrin, we can increase the paraminobenzoic acid concentration of 1.74. When it goes up to 1, then the PABA, this is short for PABA, goes up to 2.23, et cetera, et cetera. If we have this data, this is all X data, right? So this is going back to our line here. This beta-cyclodextrin concentration is our X data, and the resulting paraminobenzoic acid concentrations are our Y data. So we have all these XY data that we can plot. XY data. Then we can plot these. And here's where I'm going to bring in Excel. I guess I thought I was going to bring in an Excel spreadsheet here. So here's where we'll have our Excel spreadsheet, and we'll want to put in our X, Y data. Our X data is the beta-cyclodextrin. I think I'll put in an extra row here. We're going to use Excel here. So this is our beta-cyclodextrin millimoles per liter. And this is our Y data, which is our drug. So it's our PABA in millimoles per liter. And we have all this XY data now that we can put in to this Excel spreadsheet. So I did that here. So I put all this data in here, just copied it from the table here. So this is going to be, I'm going to insert this. So this PABA is our Y data, and the beta-cyclodextrin is our X data. So what we can do then is we can plot this data. So I'm going to plot this data right now. If you know how to use Excel, go ahead and plot the data. I am going to insert a graph. I'm going to do this step by step so you can see it. So we're going to insert a graph. So you hit insert on Excel, and then we go to our charts, and I'm going to plot XY data, and I am going to do it in where we show the points, and then also a line that would connect those points. I'm going to just move this around a little bit. I'm just left clicking and moving this around. And now we're going to select data for our chart. So you just say select data there. And so we're going to add XY data. So here we're going to do PABA concentration in with beta-cyclodextrin. Okay, and our X values are going to be this beta-cyclodextrin. So I just left clicked and dragged. And for our Y data, we're going to use our paramino, the corresponding paramino benzoic acid. And then we say, okay, and there we have drawn and we have a straight line, don't we? So there we have our straight line that shows the relationship, and I should add some I'll say okay there. We need to add some X and Y. So we need some titles, don't we, on the primary Y data, I'm sorry, X data axis. We have our beta-cyclodextrin concentration and millimoles per liter. And our Y concentration, again, we're going to, oopsie, add a chart element. Primary vertical is going to be PABA concentration in millimoles per liter. So now we know what we've got here, okay? So now what we want to do is we want to figure out what our innate solubility is. So what's the concentration of PABA when there's no drug in there? And we also want to know the slope of this line, because by using those two things together, we can determine the affinity constant, can't we? So just to remind us, this is the equation that we're using, and then we're also going to want to find out the Ka. So how do we find out what the y-intercept is? Well, what Excel can do for us is run a linear regression and get the best fit of this data here and determine what our y-intercept is here. Determine that D0, that y-intercept. And the way we do that is we can do a lot of things with Excel. I don't know how familiar you are with Excel, but if you're not sure what you want to do with this data, we know in this cell, I would like to know what the y-intercept is. Well, actually in this cell, but I'm going to label it. It's important to label things. So what I want to know is the y-intercept here. So if I don't know how to find that, I'll put in here what I think is the description. So I want the y-intercept of a linear regression, and then say go. Okay, so we can use the linist or the intercept. I usually use this calculates a point at which a line will intersect the y-axis by using best fit regression plotted through the known x and y values. So that's what I want to use. I'm going to use intercept here. And what are my known y's? So I can put my known y's in here. This is a y. And my known x's here. Here are my known x's. So then when I say okay, this is going to give us our y-intercept. So our DO, in this case, our innate solubility of PABA is this number here, 1.24. So I can just put this right in here. So I'm going to say equal to that number there. All right. The other thing I want to know is the slope of our line, right? We want to know the slope of our line. So again, if I don't know what I need to put in here, I can say, well, here, a lot of times it'll bring up other things. So guess what it says? Slope. Returns the slope of linear regression line through given data points. That's what I want, right? I want the slope of that line. And I have known y's and known x's here. And so here is the slope of my line. It's almost 1, right? 0.981. So our slope is 0.981. The slope itself, remember, is just sort of a mess. It doesn't tell us too much. But if we use the slope in this equation here, we can determine the Ka. So we want to know the Ka because it tells us our affinity, and we need that to be able to compare compounds. So if you know how to write equations in Excel, go right ahead. But Ka is going to be equal to, so we put an equal sign, and it's going to be slope divided by, okay, so we'll start with slope. So what's nice about Excel is I can just put this cell into the equation. Okay, so I want to put that cell into the equation because that's going to pull the slope for me. I don't have to put in the number. In fact, that will make it a less usable Excel spreadsheet. So equals B14, and then we want to divide that. So the way we do division in Excel is with a backslash. So that will divide it B14 by whatever comes next. And what's going to come next is the denominator here, which is our innate solubility. So I want to put parentheses around this whole denominator. So the innate solubility here is 1 point, this number here, right? And again, I want it to go to that cell and find it. Okay, and then that's going to be times, the way you do times in Excel is with an asterisk. So times, and then the quantity 1 minus slope. So we go back to this number again, don't we? And then we close that parentheses and close that parentheses, and then we have our Ka. So our Ka is 43.5699. So if we do another drug and do this linear regression and we determine the Ka and the Ka is higher than 43.56, we know that that drug is going to be preferred by the beta cyclodextrin than the PABA. If it's less than, then the PABA is going to be preferred to bind to the given into the donut or the beta cyclodextrin. All right, so we can determine the Ka and the innate solubility. So what's the power of this now? Well, there's lots of power. We can compare the two drugs, like I said, as far as affinity goes. We can also determine how much beta cyclodextrin. Let's say we wanted to have a paramino benzoic acid concentration of 10. So let's say we wanted 10 to be our concentration of drug. So what we would do is put in 10 here, right? 10 millimoles per liter is going to be equal to our innate solubility, which is this number here. I'm going to just write it out just so you can see the idea of it. Plus the slope of our line, which is 0.982, let's say, times the concentration that we need of the beta cyclodextrin. So we would solve for C, wouldn't we? So how would we figure that out? Let's see here. I'm going to make another equation. So we want to know what, so here's the concentration of beta concentration of PABA we want is going to be here, okay? And then what we want to do is say, so what concentration of beta cyclodextrin needed? Well, that's going to be equal to this number divided by well, I'm going to get back to you on that. I'm going to do the math and get back to you because I don't want to mess it up here, okay? Plus, it's been too long already. All right, I'll see you in part 2. Bye.